Today we're going to be talking about limits by algebra and trigonometric limits. Now if you remember, this example should look familiar from the previous lesson, and the reason that I start this lesson with the previous example is there's really a shorter way than using a table to find limits. Remember what we talked about in the previous lesson is all of these numbers were getting closer and closer and closer to 2. So x was going to 2 from numbers a little bit less, and x is going to 2 from numbers a little bit more. So our function values were giving us the value of the limit. So let's look at what happens. As we were getting closer and closer to 2, what were these values getting closer to? The limit, as x went to 2 from numbers a little bit less, looked like it was getting closer and closer to 1. Then, as we look at numbers a little bit more getting closer to 2, approaching 2, so the limit as we were getting closer to 2 from numbers a little bit more, well, what did those numbers look like they're getting closer and closer to? Those numbers are getting closer and closer to 1. But if you remember, when we got 2, I have no value there, because what did this give us? When we plug in this value, this gave us an error in our calculator. But let's go back to this actual function. When looking at this function, a lot of you may have recognized that what I could do was we could factor the top and then what happens? Notice how the factor of x minus 2, which made the top and bottom 0, goes away. So what happens there? The reason is we have a hole now there, but now I can find the limit as x goes to 2 of this new function x minus 1. So when I plug in 2 minus 1, we're going to get the limit value of 1, which is what our value actually was. Remember, the graph of this function would look like a line, okay, with a hole at 2. Remember, to find limits, the function doesn't have to equal that value. It just has to get infinitely close to it. So some important limit laws that we have. Okay, so when you're adding or subtracting, you can separate that limit out into each individual function. The second one, I can pull a constant out in front of the limit, so a number that's sitting in front of a value. If you're multiplying, you can multiply individual limits. Same thing with division, as long as the bottom doesn't equal 0. You can pull a power out in front, and even a root out in front. And then these bottom two are the most important ones. The limit of a constant is that constant. The limit as x goes to some value of just regular old x is equal to a. Or, because if you think about it, that function there is y equals x. And we know y equals x. If y equals x, x and y are the same thing. So you can just plug in a for x and get our value. This example, let's use limit laws. And we're not going to be doing this a whole lot, but you need to understand what's going on here when we do these limit laws. Okay, so using the first limit law, I can separate and essentially distribute this limit to each one of the pieces of our polynomial. Now, remember, there's a few key properties. We need to basically break this down so that we have the limit of a constant or the limit of just regular old x. So what I can do, a constant I can pull out in front. And remember, I can say and pull out the squared and just take the limit as x goes to 3 of x, which broke this down into this bottom property. Again, I can pull the constant of 8 out in front. So that, again, we've broken this down into this basic limit. And then here we have the limit of a constant. Okay, so when you have a limit as x goes to 3 of just x, that equals the value that the x value you're trying to find the limit of. So this is going to be equal to 3 squared minus 8 times 3. Now the limit of a constant is just the constant. Now notice how this changed from this function. I'm going to cut and paste that original function down here. That's 4x squared minus 8x plus 9. This is so important because notice how this is a polynomial that I was trying to find the limit of. Where do you find the value that you're trying to find the limit at? Basically, we're just plugging it in. When I actually find this limit, this actual value is equal to 21. So the reason I did this example, if you have the limits of polynomials and rational functions, this is super important. If it's a polynomial, you could basically just plug in the value of c in your polynomial to find your actual value. Same thing for a rational function. You can plug in your value of c in to get the actual value, given that the bottom is not going to be 0. If the bottom is going to be 0, we have to do some manipulation. Okay, use substitution. Basically what this means, we're just going to be plugging in the 3 and that gets me the same value because it was the same problem that we did before. So that's now the easiest way to do limits. But I wanted you guys to understand why it was the easy way. Because this is a polynomial, and polynomials are what we call continuous, so I can plug in the value of 3. Next example. Notice when you plug in 4 on the bottom, we would get 16 minus 8, which would be 0. So I would have 0 on the bottom. We can't have that. So a lot of times with rational functions, what you need to do is you need to first manipulate this and factor it. So let's try and factor first. And notice how I'm conveniently factoring to the factor that's going to hopefully go away. I know I have x minus 4 on the top, so hopefully I'm going to have an x minus 4 on the bottom. I do. So the x minus 4's cancel. So now we're really looking at the problem of this. And what I want you guys to actually show me, please show me the substitution of 4 minus 1 and 4 plus 2. So our limit is going to equal 1/2. Showing me the actual substitution of the 4 in for the x. Next example. Again, notice how we make, when I plug in 4, I make the bottom equal to 0. And actually, when I plug in 4 in the top, we actually get 0 on the top. We have to manipulate this. We have to manipulate by multiplying by the conjugate of the top. Now notice when I multiply by the conjugate of the top, what happens? We have x plus 5 minus 9. on the bottom, I'm not going to multiply that out. I'm going to leave it alone because I've manipulated the problem so that notice what happens on the top. I have x minus 4 on the top. I have x minus 4 on the bottom. And then I have the part of our radical. So the x minus 4's cancel. That allows me then to actually find this limit. Realize what cancels on the top is just a 1. So now I can go ahead and plug in. And we get 1/6 for our limit. Okay, next example. Use trig limits and limit laws to find the following. This is typical of a question you might see on the AP, where they're going to be asking you to find the limits of certain trig functions. First, what you need to realize, you need to memorize these two trig limits. You need to understand that those two limits, the limit as x goes to 0 of sine of x over x is 1, and the limit as x goes to 0 of 1 minus cosine x over x is 0. So our goal is to manipulate this function into these certain limits so that I can then break it down. Remember that I can separate this into certain products. So I see I have a sine of x over x squared, remember, is x times x, over 1x. So I can separate that out into the limit as x goes to 0 of the sine of x over x. Now look at what I also have. I have 1 minus cosine x over an x. That's another limit that I need. So I can break down this product into that. And then lastly, we still have this 2 hanging out. So that's going to break down into the limit as x goes to 0 of 1/2. So now let's look at what each one of these limits is going to equal. And actually showing me that work is going to be important. Limit as x goes to 0 of sine of x over x, well, that's equal to 1. Limit as x goes to 0 of 1 minus cosine x over x, well, that's equal to 0. And then lastly, limit as x goes to 0 of 1/2 is 1/2. Now because we had that 0 in there, this all simplifies to be 0. But the key thing is understanding that you're breaking it down. This middle step right here, that you're breaking it down. And showing me that that actual work is broken down. That's super important. Okay, find the limit of the function. Justify your answer. I'm going to start throwing this in more and more often. Justify your answer. Using definitions to make sure that your answer is justified. Remember our definition of a limit. Our definition of a limit was that the left side had to equal the right side. So let's find actually each one of those limits. I need to find the limit as x goes to -1 of numbers a little bit less of our function. Well, which function do I use for numbers a little bit less? This top piece is the numbers a little bit less. So I have 2 minus 3x. Since 2 minus 3x is a polynomial, I can just plug in, showing me the plugging in. So I have 2 plus 3, which is equal to 5. Now let's do numbers a little bit more. So now x goes to -1 from numbers a little bit more of our function. Now numbers a little bit more is 4 plus x squared. 4 plus x squared is a polynomial, so I can just plug in -1. That also equals 5. So it appears that our limit equals 5. Now make sure you're using the definition of the limit to justify it. So make sure you're saying that the limit as x goes to -1 from numbers a little bit less of our function equals the limit as x goes to -1 of numbers a little bit more of our function, and show me what that actual value is, which is 5. Our next example, and this is a good for you guys to realize of why we've learned limits. Average speed versus instantaneous speed. So experiments show that a dense solid object dropped from rest will fall freely according to that equation, where y is measured in feet and t in seconds. And there's certain parts of that equation you should hopefully recognize from physics. Hint, hint. What is the average speed for the first 2 seconds? So average speed, when I'm talking about average speed, we're talking about the change in y over the change in time over the first 2 seconds. So I'm looking for essentially y of 2 minus y of 0 over 2 minus 0. Hey, that's the slope of that function, even though this isn't a linear function, but the slope evaluated over these values. So I have 16 times 2 squared minus 16 times 0 squared over 2 minus 0, and that is going to simplify to 32, and I give us units, feet per second. Make sure you're giving me units. If I give you units, you give me units back. Now, what's the instantaneous speed? Okay, instantaneous. Instantaneous is a fancy word for limit. So what we're going to do is we're going to find the limit as h goes to 0. Now just let me get through the formula before you guys start freaking out. We're going to find the limit where h is some number that we're adding to the time of 2, because I'm looking for the instant at 2. So h is going to be a really, really small number that we're going to add to 2, but I'm going to make h go to 0 so that it gets infinitely close to 2. Minus y of 2 all over, well, the x value is subtracting the delta time, so I have 2 plus h minus 2. Notice what happens, the bottom just becomes h. The bottom, I just get h. Now, multiplying out the top, what I did is I just evaluated our function at 2 plus h and at 2. So, doing a little bit of math here, and now this is just algebra. Simplifying the top, I get 64 plus 64h plus 16h squared minus 64 all over h. Now what that is going to simplify to is the '64's cancel, and h is going to cancel, so I'm left with 64 plus 16h. Now when I plug in h to be 0, we get our limit to be 64, and I gave us units, feet per second. That is all we have for today. Please make sure your lesson questions are submitted on time.